So unless if there is any question with your permission, I can go to the last topic. Save usernames. So as I said, we are lucky because our last topic, which is the Lincosamides, is also a very short one. I think it has only about 12 to 15 slides. So we should be able to just finish it in the next 1 hour. So Lincosamides, and basically we will study only 2 Lincosamides, and the 2 examples we have is lincomycin, and the lincomycin is a naturally occurring one, and we have clindamycin, and the clindamycin is semisynthetic. And just like all the other antibiotic drugs we have talked about, you find that there can be a mixture, like when we were studying the macrolides, we said even when we were studying the aminoglycosides, we said the occur mixtures. You can have kanamycin A, kanamycin B, kanamycin C, even gentamicin, it occurs in a mixture. Even erythromycin occurs as a mixture A, B, and C. And normally the difference is very small, that within the main structure there could be a group that is just one group that is different within a particular position in that molecule. Like you can find instead of a methoxy group, you have a hydrogen. When we were looking at the erythromycin A, B, and C's, we saw what the main difference was in position number 12 and in position, I think, number 3, the methoxy group that is found within the desosamine sugar. So you find that the difference is so minor, but that difference, of course, will make one drug different from the other. Like you can remember when we talk about kanamycin A, kanamycin C, we did mention that kanamycin A, which has amino groups at position 2' and position 6', it becomes more active, but it is also more toxic. It is also more susceptible to deactivation by AAC or acetylating enzyme. So because of that small structural difference, you find that that component of that particular mixture can also have a difference. And more often than not, one of the components, either A, B, depending on the one which has the best properties, which can of course be changed or structurally modified to give a better drug. So even when we look at the lincosamides, lincomycin is a naturally occurring molecule, but just like all the other drugs we have said, it had its own shortcomings. It is not very potent. It wasn't very potent. It didn't have a very broad spectrum of activity, and therefore there was need for structural modification to see whether it could be structurally changed to give us a better drug. Indeed, it was structurally changed to give a better drug, and the better drug was clindamycin. And as we look at clindamycin, although not very clear, clindamycin indeed has a chloro group, which makes the drug more active, better lipid solubility, and it was found to have better activity. So you can see this was the structure. This is the structure of lincomycin. So this is our lincomycin, and you're going to see it has a unique structure. It has this pyridine ring there, but our pyridine ring there is substituted with a methyl group and a propyl group at that position. And we will see that those groups are indeed not necessary for activity. It has also an alpha-oriented carboxylic group. This was a carboxylic group before, of course, it is bound, it forms the amide bond with the sugar. So it has that alpha-oriented carboxylic group. Then it also is joined. You can see this is a very unique sugar. Very unique sugar. Very unique, in fact, because it's a thiol sugar. This is just a sugar like any of the other sugars we've looked at. Like it's a sugar just like even like glucose or anything, a 6-membered sugar. That oxygen, a 6-membered sugar. You can see that hydroxyl group. You can see that hydroxyl group. This, of course, we have put an R there because that group, that R can be substituted with different groups. But the major difference is that at this position 1, instead of it having a hydroxyl group, it has a thiomethyl group, and therefore it's a thio sugar. So that's one difference. So it has a thiomethyl group there, therefore thio sugar, but it's basically, it is just a sugar. The other difference that we can note is that when you look at most of the other sugars, they go to, like, that is position 5, position 6, and then they have a position 7, because most of the sugars at this position here, you find like CH2OH. So most of the sugars at this, you have a substituent like CHO or CH2OH. And therefore, if you have like a CHO or CH2OH, then you can say this is position 5, this is position, that's position 1, 2, 3, 4, position 5. And then the CH2 will be, because as I have said, they usually have CH2OH. So that position there would be position number 6. That would have position number 6, but most of the sugars do not have this, do not extra carbon. So you can see these are very unique sugar, that this sugar is also having actually that carbon, and it also has this other carbon. So it is an 8-membered. So it has that position 5, position 6, position number 7. So in place of the other sugars, which we know are usually up to position number 6, all actually having 1, 2, 3, 4, 5, because of these 6 carbons, this sugar has 8 carbons. So it is also a very unique sugar, in that this sugar here contains 8 carbons when you start from that position 1, 2, 3, 4, 5. That's our position 6, our position 7, and that our position 8. So that also makes that sugar a bit different from the other sugars that we see in other compounds. And of course, in addition, we have also said it is a thio sugar. So these sugar, so this sugar, and of course also when you look at it, it is also an amino sugar. This is also an amino sugar, because you can see at position number 6, 1 should have been CH2OH or CH2, yeah, it should be CH2OH. So one of the hydrogens has been replaced by an amino group. So indeed, it's an amino sugar also. So what has happened is that this group here, which is a carboxylic derivative, has condensed with this amino sugar to form a peptide bond. So it has formed a peptide bond, and that way, that is the molecule that we're calling lincomycin. And that lincomycin can be changed to a very important drug, clindamycin, because we have said clindamycin has much, much more activity. And the change, if you look at the change, is at position number 7. It's position 5, 6, 7. So at position number 7 of lincomycin, you find that the hydroxyl group is replaced with a chloro group, followed by inversion of stereochemistry. So if you look at this molecule here, you have a hydroxyl group there. If you look at this molecule here, the hydrogen is still there. If you look at this molecule here, the clindamycin, it has a chloro group. That is change number 1. Change number 2 is that the stereochemistry of lincomycin and that of clindamycin is not the same. So you find that the lincomycin is 7R. At position number 7, lincomycin has the R. But for clindamycin, at position number 7, it has the S configuration. So those two changes, hydroxyl group replaced with a chloro group with inversion of the stereochemistry, gives us clindamycin. Otherwise, everything else is the same in lincomycin and clindamycin, just the replacement of hydroxyl group with the chloro group. Hydroxyl group has higher water solubility, chloro group has higher lipid solubility, and of course stabilizes the molecule metabolism, and therefore gives that drug much better activity, and therefore and of course, as we have said, with inversion of stereochemistry from 7R to 7S. So introduction, lincomycin is produced naturally by several species of the actinomycetes, and all this. It's a clindamycin, on the other hand, it's a semi-synthetic derivative obtained by chlorination of lincomycin. Small modifications at carbon 7, which we have already seen, or loss of the carbonyl group causes dramatic alterations in lincomycin activity. So we're saying if you lose this carbonyl group here, you try to lose that carbonyl group, you would of course lose activity. If you change this position, as we have said, see in position 7, a very small change whereby you put a chloro group with inversion of stereochemistry, it gives us a molecule which is about 20 times more active than the original molecule, which is lincomycin. Clindamycin is almost 20 times more effective than lincomycin inhibiting the growth of Escherichia coli. The search for antibiotics, so these drugs, they were synthesized because there was two issues of resistance to macrolides, lincosamides, to streptogramin B. So there was two issues of resistance. So they were trying to do small structural modification in search of better molecules with better activity, and of course also better pharmacokinetics. So the development of the lincosamides was in line to look for better molecules that had better activity because of the continued development of resistance. That has been a big hindrance. That's been a big challenge to antibacterial management, because anytime you come up with a good molecule, it's good for a very short time. The microorganism changes things, then you do have a lot of resistance. The lincosamides contain an unusual, so that's why I was saying they have a unique sugar and an unusual 8-carbon sugar, which is a thiomethyl amino octoside. And I've shown you that thiomethyl. I've shown you thiomethyl. This is a thiomethyl, and this is amino. And then the whole sugar with the 8 carbon atoms, we call it the octoside. So that's what we are calling the unique sugar. They contain an unusual 8-carbon sugar, a thiomethyl amino octoside, or thiolincosamide. So that is a very specific, or a very, very specific group that is found in the lincosamides. Of course, we have not come across it in all the other drugs that we have looked at. The sugar is linked by an amide bond. Again, we have discussed that. So that sugar, the thiomethyl octoside, so that is joined to this, which we call hydric acid. So this is joined to this group through an amide bond, and that's an amide bond. So I had already explained that. I'm just going back so that we can understand. So the sugar is linked by an amide bond to an N-propyl substituted N-methyl pyrrolidyl carboxylic acid. So N-propyl substituted N-methyl. So again, I had said those groups. N-propyl, when you say this is N-propyl, it means this propyl group is an aliphatic group. It is it's a CH2, CH2, CH3. In other words, it's not branch. Whenever you see the small n, it means a straight chain, no branching. So N-propyl, N-methyl, so it's not N-propyl, it is, but this N is like a small n. N-propyl meaning the N is showing us that it's an aliphatic. Then this one is now the capital N, N-methyl, because the methyl group is attached to the nitrogen. So N-propyl, N-methyl. So it's good to understand those words. So N-propyl substituted N-methyl pyrrolidyl, carboxylic acid. And I think that is quite obvious. Pyrrolidyl, this is pyroridine. So N-propyl, N-methyl, N-capital methyl, pyrrolidyl. We call it pyrrolidyl because now we are using it as a pyrrolidyl carboxylic acid. This is now carboxylic acid. So we can't be able to get that from that. So N-methyl, N-propyl substituted N-methyl pyrrolidyl carboxylic acid. So that's what we are called, the bigger name for the whole of that group. All in very short, it's also called N-methyl, that is the N big one, N small one to show that it's an aliphatic acid. Trans, what I had told you, is also called hydric acid. So that molecule, which we also call substituted N-methyl pyrrolidyl carboxylic acid, is also known as N-methyl N-propyl trans hydric acid. Trans, I believe it's because of the this carboxylic acid, we have said can take. Remember, whenever you have a cyclic ring, cyclic rings do introduce rigidity. So because they do introduce rigidity and can introduce a geometric isomerism. So this group here can either carry the alpha orientation or the beta orientation. When it carries the alpha orientation, it looks like the resulting molecule, the resulting carboxylic or the resulting hydric acid is a trans one. Just give me 1 minute. I check on my cameras. Somebody is ringing the bell. Sorry about that interruption. So we are only saying it's a trans. There you can have the sugar, sorry, the carboxylic acid is joined through an alpha orientation. So that means this, of course, whether it's trans or cis, is just looking at the groups and knowing whether the big groups on the big side, on one side, all the small groups on one side. So once it joins with the alpha orientation, it ends up being the trans hydric acid. The lincosamides are weakly basic and form clinically useful hydrochloric acid salts. Again, that from what we have learned all along, we should be able to understand the minute you have this nitrogen there, this nitrogen is not part of an aromatic system. And because that nitrogen is not part of an aromatic system, for sure, this nitrogen can be protonated at physiological pH, or it can even be protonated through formation of hydrochloric salts. So that this nitrogen is highly basic if you compare it to this nitrogen, because this nitrogen is attached to an electron withdrawing group, and therefore the lone pair of electrons of that nitrogen are a bit pulled away. So this nitrogen is highly basic. That's why we are saying that the lincosamides will be basic in nature. They are weakly basic and form clinically useful hydrochloride salts. So we can be able to formulate them into the hydrochloride salts. Again, when you formulate them into their salts, more often than not, is just for purposes of increased water solubility. They are chemically distinct from the macrolide antibiotic, but possess many pharmacological similarities to them for sure. Their structure and that of macrolide is very different, but their mode of action very, very similar. They block protein synthesis, and because of the similarities in their mode of action, that's why we are saying they have similar pharmacological biological activity. The lincosamides bind to the 50S ribosomal subunit. 50S ribosomal subparticles at a site partly overlapping with the macrolide site, therefore are mutually cross-resistant with the macrolides and work through essentially the same molecular mechanism of action. That's what we have said, that because of their similarity in their mechanism of action, they will have similar pharmacological activity. The biggest danger is that if a microorganism acquires resistance towards erythromycin, there is no need of giving lincomycin or giving clindamycin, because similarity mechanism based. Because of that similarity in their mechanism, they can also have what we call cross-resistance, whereby once the microorganism has resistance to one of the drugs, one drug in one class, it will also have resistance to another drug in another class. So that's what we call cross-resistance. And this, as I have said, is not structurally related. This cross-resistance is not structure related, it is mechanism related, cross-resistance, because these drugs have a very similar mode of action. So if the receptor, let's say, it's blocked, or it's modified, it will be modified both for the macrolides, it will also be modified for the lincosamides, and therefore there can be that cross-resistance. The lincosamides undergo extensively for metabolism, resulting primarily in end-methylation. Again, because of this is a metabolism structure related, and the biggest advantage is at the end, this methyl analog retains biological activity. Again, going back, simple. This is this N-methyl group. Whenever you have an alkyl group attached to a nitrogen, or even attached to an oxygen, oxygen will be oxidative O demethylation. This is oxidative N. So that I think we have mentioned so many times, but the biggest advantage, that's just loss of that methyl group, of course, loss of slight of its lipid solubility, but fortunately the drug still retains, as we have said, still retains biological activity. Lincomycin, it's a 6 amino. That from, we look at the structure at the position number 6, as an amino group, 6-deoxy. Deoxy in terms that when you put the amino group, you remove the hydroxy group. So 6 amino, 6-deoxy, because in putting amino group, you have the group, which would have expected to be at that position. 6 amino, 6-deoxy, octopyranose. That is just the name of that sugar. That's the name which is given to that sugar, octopyranose, with strong antibiotic activity. To maintain or enhance this activity, one must have the configuration. So this is now some of the structural requirements, that you must have the configuration of the first 5 asymmetric carbons of the sugar residue, the thioglycolic moiety in the alpha orientation. We are saying that the orientation, the 5, 1, 2, 3, 4, 5, these groups, the orientation of these groups is very, very, very important. The stereochemistry in general, all that we are saying is that the stereochemistry of the groups that are attached on to the octoside sugar, very, very, very important for maintenance of biological activity. Yes. Yes. Nico class. So you're saying the configuration of the first 5 asymmetric carbons of the sugars residue with the thioglycolic moiety in the alpha position. So even so the orientations are very, very important, even for the thioglycolic moiety, or even that must carry the alpha. So the stereochemistry, very, very important for the biological activity of lincomycin. The nitrogen and carbon 6 with the R configuration is also a prerequisite for the activity. The nitrogen, I think it should be at carbon 6 with the R configuration. Again, we are saying that also very, very important for activity. Substitutions at the level of carbon 7 as well as the pyrolytin moiety can dramatically enhance this activity. So we have seen substitution at carbon 7, replace the hydroxyl group with a chloro group, invert the stereochemistry, and the resultant molecule has much, much higher activity. So also we will see on the pyrolytin moiety, an N-propyl group is important, or is important for maximum, or is necessary maximum biological activity. So the groups that you have in this molecule are necessary. They are necessary for optimal. If you remove them, there can be activity, but not the best. So those groups that you find in this molecule, the stereochemistry of, again, all the group in this molecule are highly, highly important for what we call optimal or maximum activity. It also serves as the starting material for the synthesis of clindamycin, as we have said, where you will have replacement of the carbon-7 hydroxyl group with the carbon-7 chloro group with inversion of R stereochemistry to carbon-7 R stereochemistry to carbon-7 S stereochemistry, as we have already mentioned. So the lincomycin is the starting point for synthesis of clindamycin, and clindamycin, for sure, we have said, has much higher potency, and it is by using thionyl chloride, and you change the 7R hydroxyl to 7S chloro with increase, not just with retention of activity, but with improvement and increase of biological activity. The substitution of the chloride for the hydroxyl group consequently makes clindamycin more bioactive and lipophilic than lincomycin, and thus it's better absorbed following oral administration. We always know halogens increase lipid solubility. Hydroxyl group increase water solubility, as we had said. So clindamycin will have much higher lipid water partition coefficient, and therefore better bioavailability. And remember, these are antibiotics. They are acting on microorganisms. So the higher the lipid solubility, the higher the rate at which this drug will achieve the minimum inhibitory concentration, because it's penetrating the lipid membranes better, and of course the higher its activity. It is significantly less painful than erythromycin when injected IM as a carbon 2-phosphate ester prodrug. This one we're going to look at the formulations of clindamycin. We're going to look at them and the formulations. So, but we are only saying it can be available, and perhaps I can still go back. So if you look at this structure of clindamycin, you can see this position. I'll put an OR. See, I have put an R here. I believe all of us can be able to see this R group here, and we are calling it position number 2 because this is position 1, position 2, position 3, position 4, position 5. So this is the position 2 of the sugar. So that's position 2 of the sugar. And obviously, under normal circumstances, you would have an OH group here, hydroxyl group. The obvious thing is that hydroxyl group can be structurally modified. This hydroxyl group can be structurally modified. And I believe we looked at macrolides with you. And if you remember macrolides at position, again, 2 of the desosamine sugar, we had the hydroxyl group. And that hydroxyl group at that position, remember, we said you could esterify it, or you could do esterification with stearic acid to get erythromycin stearate. You could do esterification with propionic acid to get erythromycin estolate, and you could also do esterification with ethyl succinate. We have done all these things. So it's the same thing to get erythromycin erythromycin ethyl succinate. And the same case applies to this, that this hydroxyl group here can be esterified with different groups. You can react this hydroxyl group or this hydroxyl group there can be reacted with different groups to get different formulations. And of course, the different formulations can have different characteristics. Just as we know, when we're looking at, again, macrolides that allow me to go back to erythromycin, we say the erythromycin ethyl succinate is a pediatric formulation, which is used as granules. When you look at erythromycin estolate, we said it is a drug that has a very good lipid solubility but of course we did say it has its own challenges of cholestatic jaundice. Then we looked at erythromycin stearate. We said it has very, very high lipid solubility. It is tasteless. It will penetrate the membranes well. It has also acid stability. So the group that you put at that particular position can have some influence on the property of the ultimate group. Yes, it is just a small group in terms of esterification, but that group can also either bring in water solubility or water solubility, and therefore give that particular resultant compound or resultant drug various or different characteristics. So you will add there depending on what kind of molecule that you want. Therefore, we are saying